So there is a much more elegant way to handle this problem, and which is the use of what are called integrated clock gating cells. So we don't want the enable to change state when the clock is high. One very simple way to accomplish that is just put a latch, level sensitive latch, before the AND gate. So the enable goes to the level sensitive latch, and the latch is transparent when low. That's what this little bubble at the bottom shows. So when the clock is low, the enable goes from D to Q. And when the clock is high, the enable does not go through. The latch is not transparent. Okay, this is a level sensitive latch. This is not a D flip-flop. It's a level sensitive latch, and it is transparent when the clock is low. So this is a very simple and obvious way to block enable from going to the AND gate when the clock is high, because the latch is only transparent when the clock is low. You don't mind the enable, the input to the AND gate changing when the clock is low. The problem is only the input to the AND gate, the enable input to the AND gate changing when the clock is high. And we have taken care of that problem by introducing this level sensitive latch, which is transparent when low. Okay. So now so now you will not have the spurious glitchy outputs at GCLK, at gated clock. So this combination of latch and AND gate is called an integrated clock gating cell, or an ICG. And essentially it blocks the enable from going through to the AND gate when the clock is high. This kind of a clock ICG, or integrated clock gating cell, is usually present in a standard cell library. And then when logic design is being done, these ICGs are used for clock gating. The ICGs also have an additional feature sometimes, which is called an ICG with test feature. So when a chip is being tested, there are various ways to test a chip. So when a chip is being tested, that is, it's not really being used and it's not operating in function mode, but it's, let's say the chip is sitting on a tester and you're testing if the chip has any defects. During the test program, when the test program is running, we cannot have the clocks being gated. The test program assumes that the clock is reaching everywhere, every flip-flop, that every pulse is going through. So we often need a feature in the clock gating cells such so that the clock goes through regardless of the value on the enable when the clock is being tested. So to do this, we add a test input to the ICG, which bypasses the enable during test. You can see here that there is a test input, okay, and here's the enable, and they go through a 2-input OR gate. So if the test enable is 1, then the OR gate output is a 1, regardless of the value of enable. And then this 1 then goes through to the AND gate, and then the clock, and since the enable input of the AND gate is now a 1, the clock will just go through. So when t is 1, the clock will simply go through the GCLK regardless of the value of enable. And this feature is required in order to test the chip. Okay. This 2-input OR gate can be either before the latch or it can be after the latch, and both varieties of ICGs are used. Okay, it's a matter of personal preference. So you often have ICGs with this additional test input, and the only purpose of the test input is so that when you are in test mode, when you're testing the chip, you send a value of 1 to the test input of all the ICGs, and that basically makes all the ICGs let the clock go through, and all the clock pulses go through. And when this chip is being actually used for its functional purpose, then the test T signal will be kept low. And so then the enable takes control. So standard cell libraries will have ICGs with this test feature and even without the test feature. And it's up to the user or the designer to decide whether they want to provide a test feature or not to the ICGs in the circuit. Normally, we always provide that feature because all chips usually need to be tested. And again, during testing, we don't want the clock gate, the circuit's gating clock to actually gate the clock. We want all the clock to go through everywhere during test. So that's why you have this test feature. There's no standard symbol for an ICG. We will use the following symbols for ICGs in this class. And so it's just like it's basically the same as a symbol for a latch. And what I have is a C input for the clock, a CG output for the gated clock, and an enable input. That is the functional signal that determines if the clock pulse will go through or not. So you have, again, like I said, there are two possible types of ICGs. One is without test input and the other is with test input. And so this is a symbol we will use. Now, ICGs and standard cell libraries most standard cell libraries contain ICGs. In the .lib, ICG cells and only ICGs will have the attribute clock gating integrated cell defined. So if you do a grep for clock gating integrated cell or just clock gating in the .lib, you will see if the standard cell library has ICGs, you will see some lines being produced as output by the grep command. And this clock gating integrated cell attribute can have different values to indicate what type of ICG it is. So if it's an ICG without a test input, then the clock gating integrated cell attribute would be set as latch pause edge. And then you can have latch pause edge pre-control attribute value. So that's when there's an OR gate at the input to the latch, or latch pause edge post control when the OR gate is at the output of the latch, between the latch and the AND gate. So you can tell from the .lib what type of ICG the cell is. And in one of the homework assignments, I will ask you to look at different standard cell libraries and find out what are the names of the ICG cells and what type of ICG cells you have in the library. And when you do that assignment, you will need to know that you have to search for this clock gating integrated cell attribute that will only be defined for ICG cells. All other standard cells will not have this attribute defined. So that's all for this session. Thank you.